Hello, good morning. Can you hear me? Okay. So I think it's about time to start our training course today. We welcome all professors from different university, different country, and students from every lab. I think we will start the meeting now. So first talk will be given by Jonathan, right? Okay, so let's start it now. We will keep a record on the WebEx, and we will share you all the link later. So everybody, please to remember to mute your microphone. Then we can start it now. Thank you.
Okay, good morning, everyone. My name is Jonathan. I'm a professor and students. Today we will have 3 sessions. The first session is about ODU, architecture, interfaces, and the installation. And then we will talk about the Fronthaul interface. And then we will, and the third session we will about intelligent controller. So the first session is about, I will start the first sessions, OpenRAN, distributed unit, architecture, interfaces, and installation. So this is the outline of our first session. The introductions, then we will talk about the architecture and the interfaces, and then Tony will tell about the scheduler, and then the last one will be presented by Nadif about the installation. Okay. So I'm sure nowadays everyone has their own phones, and I'm sure that nearly all of you using 4G connections. If you have 4G connections, means your phone is connected to the base stations, which owned by the network provider. So for example, here the phone is using service from Chunghwa Telecom, means that this phone is connected to the base stations owned by the Chunghwa Telecom. This is the overview of the infrastructure on network owned by the network provider. We can see the infrastructure as 2 parts. The first part is the access network. This part is the access network, and then we have the core network. The access network is part of the network that gives user access to the network, and we usually see this equipment is easily. Maybe we can see it in the streets or on top of the building. And then the core network is part of the network that connects the different parts of the access network and provide gateway to other networks. Usually we didn't see it directly. And we also have another part which is called as backhaul network. It's basically connecting the access network to the core network. In this presentation, we will discuss a lot about the access network. So this is the access network for the 4G LTE network. Especially we call it distributed RAN. So basically the access network is distributed to the sites. In LTE network, core network part is called as evolved packets core, and the access network is called as evolved node B. and sometimes we call it inode B. So the inode B consists of two parts. First one is the BBU, and the second part is the RRU. BBU is the baseband unit, which process the digital signal, and RRU is the remote radio unit, which process the radio frequency signal. So then, to reduce the cost of the network, the provider try to change the architecture to they decentralize the BBU inside the BBU pool, so they can reduce the operational expenditure and the capital expenditure. And using this architecture, we also can enables the resource sharing. So maybe at one time the BBU has some problem, and we can like change it, and yeah, it's easier to deploy. So in this part, we want to the provider and the vendors trying to virtualize the BBU, so they change the BBU to run on the virtual machines, and then they also this part is for the future connections. They try to distribute like disaggregate the run to BBU to DU and CU. So the CU is where the less time sensitive packet processing functions, and the DU is for the real-time baseband processing functions. DU can be centralized or located near the cell sites, and the CU and DU could be virtualized, but some of the vendors still selling it using their proprietary hardware. Then they also try to improve the disaggregation. So they divide the control plane and the user plane, so they can have flexibility on the user plane. So maybe at one time the bandwidth will be very high, and they can just expand the bandwidth by adding more CU user plane functions. And using this architecture, they also can optimize the user plane for specific services. So this one is the OpenRAN solutions. Basically, we tried the second level disaggregation, but we try to make it more intelligent using a device that called RIC. For the RIC part, we'll be talk more deeply on the third session. And OpenRAN also try to make the API or interface in this architecture more open. So they try to make more vendor to go into this industry, and it hopes to lower the capex and make the supply system more competitive and also more innovative. So basically, this is how the OpenRAN organization. So OpenRAN organization maybe. This part. This is the OpenRAN association or organization, which produce the specs, and they are mainly consist of mobile network operators, vendors, or some academia, and yeah, they produce the specs, and they also provide. They have another organization that call as OpenRAN software community that that make the prototype based on the 3GPP specs and also the ORAN specs. So yeah, their prototype is what we will discussing in this presentation. So this is the OpenRAN architecture. I want to highlight 4 parts in this figure. The first one is the non-real-time RIC, and then the near real-time RIC, then the CU and the DU and RRU. So the non-real-time RIC is basically for management functions and also doing the machine learning training because we want to make the RAN more intelligent. And we have the near real-time RIC, which doing the radio resource management and also case management and more controls. And we also have the multi-radio access technology CU, and then we also have the DDU and RRU. DDU and RRU is doing the layer 2 functions and doing the baseband processing and radio frequency processing. Okay, next part is the ODU architecture. So this is the high-level views of the distributed unit part. So the distributed unit part connected to 4 other subsystems. The first one is near real-time RIC using E2 interface. Then the centralized unit using F1 interface, which is divided again into F1C and F1U. And it also connect to SMO using the ORAN interface. And the last one is connect to the radio unit using Fronthaul interface. For the E2 interface, maybe the third session will talk a lot about it. Yeah, and the Fronthaul interface will be talked deeply at the second session. So this is the high-level architecture for the ODU high. So the ODU consists of three layers and divided to functional blocks. The first functional blocks contain the RIC layer and the MAC layer, and the layer 1 functions contain the hi-fi. So this is the functional blocks of the ODU high, especially. The first one, it has the ODU OEM agent, which is like an agent to connect to the SMO, yeah. And we have the F1 AP, which connect to the CUC, or it's for the control plane for the CU, and the F1U, which doing the user plan for the CU. User plan is placed where is the head that we use for data transfer, and the CU, the control plane is for the controlling things. And it also have the RIC part and the MAC part, and they also divide the scheduler and the MAC. This part maybe will be taught deeply by Tony. Based on the source code that we already try to read, this is the high entities that it has currently based on the RADISys source code. It has the CU part and the CU file stub and the RIC stub is basically a simulator. So we are focusing on the high part on the RADISys source code. And this is the thread architecture for the ODU high, because the ODU high using a lot of functions that they need to run simultaneously. They divide it to several threads. The first thread is for the overall ODU. The second thread is using for the DU app and some handlers such as configuration handler, HTTP and GTP handlers. And HTTP is used for F1IP and handler, and the GTP handler is using for the F1U handler. And they also have the RIC uplink and RIC downlink and RIC uplink. They divide it because they need more processing at that part. For the thread, they also have the fifth thread, which is for doing the HTTP handling, and the other part is the lower MAC handler. And this is the processing blocks for the layer 1, the ODU low. They have the channel processing, which is here, and the uplink task scheduling and downlink task scheduling. And because they need to connect to the ODU high, they have the FAPI procedure things, and also they have the timing events, and also FEC acceleration process. FEC acceleration process is for forward error corrections, which is for controlling error, because the radio access is using the OSC communication channel, so they need to make sure the data process is not corrupted. Actually, the FEC is done in the FPGA. This process is doing the acceleration, requesting and receiving the request from the FPGA. And then we also have the Fronthaul interface processing. Okay, next part is the interface. So this is how the ODU high has interface, ODU interfaces. So we divide the interface into two parts. The first one is the external interfaces, and then also the internal interfaces. The external interfaces, there is the ORAN interface, which connect to the SMO, and E2 interface, which connect to the near real-time RIC, and also we have the F1 interfaces here, and actually we also have the front-end interface. And for the internal parts, we have the like RIC interface and also the FAPI or layer 1 and layer 2 interface. So first one, we will talk about the F1 IP, especially to the MAC interface. So the F1 IP handler, it's used for the message from or to the CUC. There are three categories of the message. The first one is the MAC cell specific APIs, and then the MAC UE specific API, and then MAC channel specific API. So the MAC cell specific API is used for the cell level. They use for the start and stop, and the UE specific API, they have the UE create request, configuration and delete. They also have the random access channel resource request and release, and UE reset and synchronize indication. For the channel specific API, we have the uplink CCCH, and the downlink part, we have the downlink CCCH, PCCH, and broadcast request. And this is for the F1 IP to RIC interface. It's also same like the previous one. It's for message from or to the CUC. For controlling the RLC, they have for the message we have the UE create request, configure and delete, reestablishing UE request, and downlink and uplink RIC message transfer, message transmissions, reach, and RIC message delivery report. And then this is the layer 1 and layer 2 interface. For the they have two kind of deployment. The first one, if the deployment is on the same host. They just use FAPI. So the MAC layer will connect to the file layer using FAPI, and for the different hosts, the MAC layer and the file layer will connect with using NFAPI. And this part is the RIC MAC interface. We divide it as the downlink part and the uplink part. For the downlink part, for RIC to make we have the buffer status in the RIC to get the buffer status in the RIC. Then we have the schedule result report to the RIC. So after make the schedule result, they will send the schedule report to the RIC. And also we have the downlink data from the RIC to MAC. And then we also have the MAC to RIC uplink data. So next part will be presented by Tony.
Good morning, everyone. My name is Chen Yutong. You can call me Tony. I'm first year student of BMW Lab. Now I will start to present the schedule. So first, I will simply introduce the scheduler. I believe everyone knows the scheduler is a mechanism at the layer 2, which helps the base station to allocate the resource to users using algorithms. And the scheduler do the scheduling according to the reports like the CQI indication and the HLQ indication. Why the scheduler is important to 5G NR? I believe that's because we need to higher the network efficiency. Because by scheduler, we can efficiently allocate the resource to users to higher the throughput and higher the reliability. Also lower the latency and manage the power. And to design a good scheduler, developer will face some challenges. First, like how to design intelligent and efficient scheduling. As Lester slide said, to higher the network efficiency and improve the network performance, we need efficient scheduling algorithm to achieve the goal. And on the other hand, flexible and free designing platform is also important to developer, because a good designing platform can reduce the cost and higher the efficiency of the development. Like the OAI, the open air interface provided by the URLC, or the ORAN. What we present now is another platform which with full potential development. And now I will start to introduce the ORAN scheduler. You can see the right side picture is a very simple architecture of the relationship between the scheduler and MAC layer. The scheduler is at the layer 2 as the same as MAC, and it connected to MAC using the API defined by the ORAN. And we talked about the OAI previously, but what difference between the OAI and ORAN? You can see left picture. The scheduler is as a component of the MAC in the ORAN architecture, but in ORAN architecture, it's separated the scheduler as an independent function, like the right picture shows. And the scheduler connect to the make using the specific API defined by the ORAN. And the ORAN also define the DU app to manage and control all of the function block in the DU part, like the right picture set. So this is different between OAI and ORAN. And now I will deeply to talk about the scheduler architecture. You can see that on the figure, scheduler has several function blocks. We will talk about them one by one. First is the downlink and uplink resource scheduler, correspond to of the time domain and the frequency domain scheduling, and the downlink uplink adoption. Downlink uplink adoption performs per UE link adoption in downlink and uplink. And then is uplink transmits power controller, performs closed loop uplink power control for PUSCH and SRS and PUCCH. And the downlink MIMO mode control that might per UE the MIMO mode. And final function, the timing advanced manager, to estimate the TA command for UE based on the feedback from layer 1. So that's all function block in scheduler. And we talked about the API previously. ORAN define specific APIs because to make the third-party scheduler vendor can decide the layout on scheduler more open, and to ensure any scheduler implementation work with any Mac. And there are two ways in the APIs. One from Mac to scheduler, another from scheduler to Mac. And both of the API types, we classify them into two types. One is common API responsible for the broadcast and the random access procedure. And the dedicated APIs responsible for the UE specific transmission. And now we will briefly introduce them. From Mac to scheduler, a common API includes sale management request APIs, RIC indication, RIC resource request and release, and the paging indication. For dedicated APIs, it includes the UE management, scheduling request indication, uplink downlink HARQ indication, and uplink downlink SQL APIs. Also, the URLC buffer state export and the report indication. From scheduler to Mac, it also has common APIs, includes sale management response API, the IR information, downlink broadcast allocation, and the downlink paging allocation. And the dedicated API includes UE management response APIs, uplink downlink schedule bytes, and the downlink control channel information. Those API has corresponds request API from the Mac. So scheduler just responds the corresponds response API to Mac to for the request from Mac. And that's all about the ORAN schedule part. And now I will start to introduce, talk about our lab future works. our BMW lab plans to design the URLC scheduler. The URLC means the ultra reliability, low latency communication. The service which we can simply define the requirements: high reliability with 99.999% reliability, and the low latency less than 1 millisecond. And why we want to design a URLC scheduler? Because in future 5G and all, many URLC use cases will need the URLC requirement, like the AR/VR, healthcare, and the V2X. That's why we want to focus on the URLC scheduler. To decide the scheduler support the URLC, we will face some challenges, and I classify them as two parts. One is reliability requirement. We will face the interference and the channel state and coverage and packet dropping. And for latency, we will face the transmission delay, queuing delay, processing delay, and retransmission, which we will need to figure out how to solve. And we search several papers from the IEEE, and I think I will decide the URLC scheduler based on these two algorithms. One is low complexity hierarchical join multi-cell scheduling. Another is low complexity heuristic scheduling. We first introduce the algorithm 1. Algorithm 1 has a very simple concept. By the RIC architecture, we pair the suitable cells to the users according to the CSI report. As the figure shows, we can see the user 2 and the user 5 will both send the CSI to the cell 1 and the cell 2. So we can pair the suitable cells to these two users according to the CSI report if they achieve the requirement. So assume the user 2 provide the accepted CSI to cell 1. So we will pair the cell 1 with user 2. On the other hand, the cell 2 will accept user 5 because the CSI from the user 5 achieve the requirement. So our resource allocation will like this. The user 1 and the user 2 belongs to the cell 1, and the user 3 to 5 will belongs to the user 2. It is very simple concept to design a scheduler, but this algorithm it doesn't consider the interference on the cell edge. Past interference, like the intercell interference. We know the user 2 and the user 5 on the cell edge, like the scenario 2. And this scenario will cause very easy to happen the interference. So we try to consider the interference management, or you can call ICIC concept, to add this concept into the algorithm 1 to enhance this. And the cell 1 and the cell 2 will exchange the message by the X2 interface. So it will help us to do the inter-cell interference management. And originally, resource allocation will, like the figure shows, the user 2 and the user 5 will allocated a full resource block at the same time. By using the interference management, the user 2 and user 5 will allocate the different set of the resource block. So then we can avoid the interference when they on the cell edge. I think the interference management can help us to higher the reliability of the services and to enhance the disadvantage of the algorithm 1. And this is the first algorithms we consider. And the other algorithm, the complexity heuristic scheduling, we plan to multiplex the EMBB and the URLC services because in 5G NR, some services will not just need the URLC requirement, but also need EMBB because like the AR/VR or the streaming, something like that, will need both of the EMBB and the URLC. That's why I want to use the algorithm 2 to be our another scheduling design. And the algorithm 2 also has a very simple concept like the algorithm 1. First, we calculate the SNR from the reported of each resource block, and we can get the best SNR to the users. So, and we also give the URLC users the higher priority than the EMBB users. So we will first allocate resource block to the URLC users. Like this, the URLC user 1 will be allocated first, and then we continue to calculate the best SNR and also allocate the resource block to the URLC users and loop the resource allocation also to the EMBB users until all of the resource block will be allocated. And this is the concept of the algorithm 2. And furthermore, I want to add the concept of the part 3 resource of the EMBB users because originally algorithm 2, it doesn't consider if we allocated all of the resource block, but what if new users URLC want to be allocated? In some scenario, URLC users will suddenly need to transmit data, and we don't want to waste any time to the URLC users. So I consider the puncturing concept into the algorithm 2 to enhance this scenario. So by the mini slot defined in the 5G NR, we allocated the puncturing resource to the new transmission users per mini slot. So the new, after the resource allocation, the new resource block allocation will like this. The red part means the puncturing resource of the EMBB. users. So then the URLC user 3 can be immediately be allocated the resource block for that to transmit the data. This mechanism will enhance the collaboration to higher the reliability and of the URLC users. And I think this is all about our BMW future works. So next will be Nadeef to introduce the installation of the ODU. Thanks.
Good morning, everyone. Can you hear me? Hello?
Yes, we can hear you, Nadeef.
Okay, thank you. Okay, so now only for a moment. Maybe this is more about the installation status of ODU in our lab. We will not go into detail about each command. Okay, so next slide. So for now, this is the prerequisites when we install the ODU low. We set up a server using a CentOS 7.7, which is stated on the ODU low website to use CentOS 7.7. And then we needed an ICC compiler used to compile the application. And then this is one of the most important part, which is one of the most important thing in ODU installation, which is to set up DPDK in the server. So that because to use ODU, we need to have a low latency server. We need to have a high efficiency and high throughput packet offloading. So because DPDK libraries give us this access to have a higher latency offloading packet, we need to use DPDK. And then in the end, we're gonna need to set up Google Test too. All the detail of the command how to install all of this is on the link on the web on the PPT. I put up a link on the PPT, so if you're curious, you can see to the link and go and see each the comment on how to install all of this. Next. So the first thing after we set up the server and the prerequisites and all the library, before we set up to ODU, we need to install the Fronthaul library, which is provided by the ODU low. So the Fronthaul library will be explained more after this. But this is the Fronthaul library that is given by ODU low. So this Fronthaul library will perform uplane and cplane function within ODU and ORU in the future. So the way how this works is, for example, we use two server here, the yellow one, the yellow box, two server. One we install ODU and one we install ORU. The way how these two server will communicate is we create two virtual function on the network interface. One is for the control plane, one is for the user plane. And then we bind the network interface with VFIO PCI driver so that we can use the interface with DPDK. And then we will install the Fronthaul library so that this ODU and ORU can use the Fronthaul library and DPDK to send data to each other using the virtual interface. So this is what's the Fronthaul library will use in the future. But for now, for our status now, we haven't really used two server. We still use one server. So we set up ODU here, and since ORU, I don't think ORU real application is available. So we use a sample application, kind of like ORU stub application. So we set up ODU and ORU sample application in one server, and then make them connect to each other using the virtual function too. But we set up everything in one server for now in our lab. So in our lab, we still haven't used two different server and set up everything one by one. But this is the Fronthaul library in ODU low. Okay, and next. After we set up the Fronthaul interface, which is to connect ODU and ORU, we're gonna set up a WLS library. This WLS library will be used to support connection from between ODU low, FAPI, translator module, and ODU high, or L2, L1, and FAPI. So this library is a library that supports shared memory and buffer management. So the reason why ODU low and ODU high will use this and FAPI will use this is so that these three components can share at the same memory zone from DPDK perspective. So because they use the same memory zone, there will be less data exchange because they just use the same place and they can take each other data easily. So because there is less data exchange, it will be faster for all of these three components to run. And the way to set up the WLS library is to build the WLS library, and ODULO also provide L2, FAPI, and L1 stub application or a sample application to test the WLS library. So yeah, WLS library is just library to support to make them share memory and buffer management. Okay, next. And then, so the support library, the Fronthaul library, and the WLS library already been installed. We now focus on the L1 application. So from ODULO repository, they provided the FAPI translator module and the L1 application and a L2 sample application to replace ODU high because ODU high is provided by in another repository. So before we go to L2, we now will test the L1 and the FAPI first. So also each comment will be provided in the link. The simple one is we first gonna build the FAPI translator module, and then the L1 application is already an executable, so we don't really need to build anything. It's already built and compiled by Intel, so we just have to run the application of the L1. So after we run the L1 application, the L1 application will default use the WLS DPDK by itself, the one that we already installed before. So we have to make sure the WLS and DPDK is set up and running perfectly. So after we run L1, and then we run the FAPI translator, the FAPI translator, and then we run the L2, but only a sample application provided by ODULO. And after we run three of them, we test each other sending data, which in our lab, we already succeed and get some result of between L1 and L2 sending some data. And all the result and all the comment will be on the link on the PPT. So please next. And because we already succeeded in setup L1, we now move on to L2. And for L2 itself, the prerequisites is only some library that is available on Linux. So you can set up L2 not only on CentOS. I think you can set up L2 on Ubuntu too. But for L2, because we set it up on the same server where we set up ODU, we use CentOS 7.72. So the prerequisites library for L2 is the GCC compiler, the LKSCTP, which is a library that gives application to access SCTP interface, because we're gonna need to use SCTP for L2, which will be explained later. And then PCAP library. And after, so there's only 3 library that we need to set up for L2, which is simpler. And then after that, we just have to build the application one by one, which is, so the application which is provided by ODU High repository is the application itself, the CU and RIC stub to replace the real CU and RIC. And so please next. So after we set up everything, we set up the library and we build the application. Now is how we can run the integration between L1 and L2. Because if you remember, before L1, it only use L2 sample application, right, to send data to each other. But we because L2 is already built for integration, we can replace the L2 sample application with ODU High application, which is provided by ODU High repository. And so for how we can run and the integration is, we first have to assign a virtual interface for RIC, CU, and L2, which the interface and the IP address is on the link. Will be on the link on the PowerPoint. And the reason why we have to assign a virtual interface is because these 3 will connect to each other using SCTP. And they use a fixed IP address and a fixed virtual interface. So we need to assign a virtual interface too for these 3 so they can connect to each other before we run them. And then this is number 2 and number 3 is the same one as how we run L1. We execute the L1 application and then we execute the FAPI translation module. And now, instead of running the L2 sample application, which is provided by ODU, we replace the sample application with the real ODU High application. And to run the ODU High application is we execute the CU stub, RIC stub one by one, and then finally the ODU High application. And for our status in our lab now, we already successfully finished the integration and get the result. All the result and all the image is provided in the link. So if you're curious, you can see that out. And then next. Yeah, so I think that's all from me. So that's the installation status for ourselves. We finished integration between ODU Low and ODU High on one server. Thank you very much.
Okay, that's our presentation for the first sessions. Now we are open for question. If you have question, you can write on the chat.
Okay, anyone, if you have question, please ask. And maybe while waiting for your answer, for your questions, I would like to remind. Sorry, I forgot to introduce myself. My name is Ruki Harwahyu. I'm a lecturer in computer engineering, Universitas Indonesia. For those of you who are coming from Universitas Indonesia, which are candidate for this internship, please take a good time for this the first session over here, because I guess this will become a very good foundation for all of you to understand what we will deal in the internship if you are selected to be the participant for this internship. And then maybe similar to Jonathan and also Nadif, both of them are previously from Universitas Indonesia from computer engineering. They also start from nothing. They start from scratch in understanding this concept. I guess it is similar to most of you from computer engineering. Meanwhile, for some of you from electrical engineering of University of Indonesia, maybe you already have some basics in terms of layer 1 and layer 2 telecommunication system, but maybe you are lacking the basics of programming and also the systems installation, etc. So I hope from this training course you will get better understanding, better bird view or high level view of the system, and that's why I really encourage you to ask questions, whether it's basic or whatever. You just ask. Maybe let me open the first question. Is it okay, Jonathan?
Okay.
Yeah. Regarding the installation, maybe this is the closest one for I think, yeah, for to be implemented by the intern students. Maybe we would like to replicate what the MW lab already have. We would like to replicate it in UI. And for that, can you explain a bit about the hardware requirement? Like, for example, Nadif just mentioned about the C compiler. Should it be only Intel? Can we use AMD, for example? And yeah, something like that. More technical hardware issue, please.
Okay.
Hello. Sorry,
Yes.
Mr. Ruki, can you repeat the question?
Yeah. Can you explain the hardware requirement in terms of the hardware, the simple hardware, what we should buy or what we should provide, how many CPU or how many what kind of network, and can we use AMD device instead of Intel device?
Oh,
Yeah.
I think for ODU high itself, for ODU low and ODU high, as far as we know, the server is not. We can use any server. I think the important thing is, of course, I think the important thing that the hardware that we have problem is only the interface. So the interface, we have to use a network interface that is compatible with DPDK. We can search that up on internet. Network interface that is compatible on DPDK, because not all server.
Sorry, Nadif, you mean network card?
Yeah, network interface card. Yeah.
Okay. Yeah.
That's the only one that is, I think, important, because DPDK is one of the important things in the installation.
For the
And
rest,
then
we can use general purpose PC, something like that.
yeah, general purpose server, we can use that. So we don't really have to use a special server or anything like that. And for the hardware requirement itself, like how many RAM we need, how many CPU we need, it's stated in the ODU website. So we can look that up on the website.
All right.
Like but I think the most important thing is only the network interface card. So maybe for information, the one we use is I40E. That is what is recommended in the ODU website for the network interface card. It is called I40E.
Okay. So it will be safer if we just use what they recommend, right?
Yeah.
Can I ask more questions?
Okay, sir.
Yeah. Thank you. Regarding the scheduling, you mentioned that sorry, who was the name? The presenter name I forgot.
Tony.
Tony, yeah, Tony. You mentioned about best SNR. Does it means user with best SNR, or maybe it's connected to multiple base stations, so you choose best SNR from that?
Yes.
Or what?
Sorry, sir. Can you repeat the question? Because
Yeah, in some of your explanation, you mentioned that firstly you prioritize the URLC, right?
Yeah.
And then if we don't have any URLC device, then we will start to schedule the MMPC devices. And firstly, we will prioritize those who have best SNR, right?
Yes.
So in this scenario, what about the moving IoT devices? For example, for smart connected vehicle scenario, maybe we have some devices that are moving. That's why maybe their SNR is not constant. What we will do about that?
How do we do this?
Up and down. Now I don't consider too deeply about it. I think the scenario will be a challenge, and the goal what we want to figure out and solve. Yes. Maybe in future we will to think about how to design the a good scheduling to solve the scenario what you said that. Yes.
Okay. So BMW Lab currently have two types of scheduling, right? And how far did you already implement them? Have you already, for example, already modify the code of ORAN and then to implement your code, or you already implement it in terms of simulation and get some results, or what? Can you tell us about that more?
How deep we already changed the code from the ORAN and the ORAN?
For now, we just search the paper and to find the based on the concept to think about how we can design the schedule, but we are not yet start to implement and modify the code because we still chasing the ORAN source code now. Yeah.
Okay. Yeah. Thank you very much. I think
Orange.
that's all.
Sorry. Yeah, if
Yeah.
we see the orange source code, maybe currently they haven't finished the scheduling part. Say they just have UE attached procedure.
Yeah.
It's different from the OAI code.
Oh, okay. Okay. So themselves don't have the scheduling part finished yet, right?
Yeah.
Okay. Okay.
Yes.
All right. Thank you very much. So I hope some of my students can also ask if you have something in mind.
Okay.
I would like to ask a question, please.
Okay.
Hello, good
Rahmat
morning,
Mulyawan.
everyone. Yes. Thank you for the presentation. Very good presentation. I'm from ITB, Indonesia. There are some of my students here, I believe, that will take the internship in NTUST as well. So we hope to learn from you and from UI fellows as well. Yeah, good morning, Pak Ruki. Nice to meet you.
Good morning, Kak Rahmat.
Yeah.
I hope
So,
sometime in the future we will meet.
hopefully, Pak, yeah.
Yeah.
We really want to, we're really glad to do some collaboration in the future, hopefully. I would like to know how the OpenRAN software, in this case OSC or ODU, in this platform interplay with OAI, for example, or other open source platform. Because I'm still new to this platform as well. How will it interplay with other like Mosaic 5G or OAI in the deployment or in the experimentation? Maybe you can give some overview about that. Thank you.
Okay, let me answer this question. For now, we have two open source projects in parallel. One is OAI plus Mozart 5G. Another one is OSC, ORAN Software Community. For this project, for this internship, we will focus on OSC. The concept of OAI and Mozart 5G will be adapted, and we will consider to use the concept they already implement in their system and try to implement it on OSC. Because for OAI and the Mozart 5G, actually they did not follow the ORAN specification at this moment. So it may take some time for them to provide the interface. So at this moment, we are not able to connect both of them. Thank you.
Thank you, Professor A. Okay, so what I understand is we are developing both of these platform, but we take like the design philosophy or what is it from one platform to the other to make a full system in the future.
Yes.
Is it right? Okay. Okay. Thank you, Professor.
Okay, we will answering the question from the chat. So, okay. The first one is from Vincentius. Can you tell what FAPI does? And okay, FAPI is basically interface between the Mac and Phi. I should. Oh, okay. It's responsible for the data transmission between the Mac layer and Phi layer. So if you want to know more about it, maybe you can try to go to their website in the sponsor forum. Okay.
Jonathan, I think it's about time to move on. I will try to answer the question, please, by myself directly on the chat board, so you can move on. Thank you.
Okay. Suwa. From that. Okay. Thank you. For the next presentation will be from Suwa.
Hello? Hello, can anyone hear me?
Yes.
So let's begin my part. My name is Shuhua Liao, come from BNW Lab, professional student, and my topic is to introduce the ORAN Fronthaul interface. So there are 4 parts in my topics, in my outline. In the overview, I will introduce where is the Fronthaul interface in ORAN. What is Fronthaul interface? Is there any difference about the Fronthaul interface when we compare to the next generation RAN? If yes, what is the difference part? Then I will introduce. There are 4 planes in the Fronthaul interface. There are control plane, user plane, synchronization plane, and management plane. So let's begin the overview part. So from the top to the bottom is for CU, DU, and RU. So where is the Fronthaul interface? It is the interface between DU and RU, and there are 4 planes in the Fronthaul interface. For the control plane, they will transmit the scheduling or beamforming commands. For the user plane, they will transmit the IQ data from the user. And synchronization plane will do the clock synchronization. And for the management plane, it will provide a variety of ORU management functions. And you can see here, this is the function in the high file, and this is the function in the low file. And you can see that in here, it has the precoding part, and in RU, it also has the precoding part. And in Fronthaul interface, they define when the precoding part is in ODU, so they call category A RU. And if the precoding part is in ORU, they call category B RU. So why we try to use the Fronthaul interface in ORAN? What is the problem in the previous RAN? First, I will introduce the distributed radio access network, DRAN. In the DRAN architecture, the whole base station is located at the cell tower site, which means PBU and RU are not very far from each other. And for RU, it can do the jobs that receive the analog data sent from the RF antenna. And in the other hand, PBU will handle the digital information about the baseband processing. However, you can see that in here, DRAM is very simple. It's just one PBU connected to one RU, but it will present many issues from the telecom's perspective. How can we manage lots of space of the PBU? So to solve this kind of problem, DRAM evolved to CRAN. In here, all the PBU will be grouped up together as the PBU pool. Here. which can enhance the performance such as the coordination of intercell and interfrequency. Also, we don't need too much space of the installation of equipment, and it can provide cost benefits. However, despite its appeal in CRAN, it don't have the sufficient spec for Fronthaul interface. As a result, there are many specs by different vendors, so it is very hard to connect with each other. It means in here, if the BBU pool is proposed by the company A, and if RU here is provided by company B, so they cannot connect to each other. And the key obstacle is the adoption of the serial architecture. Is the large requirement of bandwidth. So how can we solve this kind of problem? In ORAN, they just want to use the functional split to reduce the requirement of the bandwidth. And they try to use split option 7.2 to solve this kind of problem. And why they try to use 7.2? I think they don't have the accurate answer. They just want to make the balance with the RU implementation and the requirement of bandwidth and then they try to simplify the RU and reduce the bandwidth, and they just choose split option 7.2. So in ORAN, they also provide the quality of service. In here, you can see the COS. COS is a parameter used in data to differentiate the types of payload contained in the packet. So the purpose is, after knowing what kind of packets are being transported, it can assign priorities to the data. Like, I think everybody know in 5G, there are 3 scenarios. One is for the URLC. In URLC, you need low latency. So for the low latency device, it can change the priority, and it will have the better chance to be handled first. And the next part is control plane and user plane. So this is the transmission model about the control plane and user plane. And for the red part, it is for the downlink, and the blue part is for the uplink. So how can the packet being transmitted over the fronthaul? They define some protocols, like in the control plane and user plane, fronthaul interface support a protocol stack that transmits signals used by EC3 or radio over Ethernet, directly over Ethernet or UDP. And the key point is, unlike CRAN, a number of transmission protocols are under investigation, such as CPRI, OBSAI, ORI, and other protocols. But in ORAN, they just define they use EC3 and radio over Ethernet. So you may have the question about what kinds of information will be in the transport header of the EC3 or radio over Ethernet. So it will provide the basic data routing capabilities, including what is the data flow type? Is the data flow is for the control plane or for the user plane? Or is this to the data concatenation? It means if it allows multiple EC3 messages in a single Ethernet payload. and it will provide the sequence numbering and the port identifiers. It means I can know the transmission port or the reception port of the DU and the RU. So after filling out the EC print message in here, it can fill out in the payload of the UDP, IP, or the Ethernet. So in about the EC print message, it will be included in the payload. So how can they transmit the packet between ODU and ORU? Because due to the nature of this message, they need to have the very strict delay constraints. So it is assumed that egg policy in here are not possible. So first, no matter downlink and the uplink, ODU will send the control plane message here, the red line. And you can see that in here they have two red lines. It don't mean the same same symbol need to transmit many times. It just means the fragmentation, and I will introduce the fragmentation part in the next page. So after ORU receive the downlink control plane message, it will have some time to process the receiving data, and he will know, oh, it will have the user plane message for the downlink to come. And for the uplink, DU will send the control plane message through the Fronthaul into ORU, and ORU will transmit to the antenna in this period, and after it processing, RF antenna will transmit over the RU, and then transmit the uplink user plane message for symbol M. And for here, you also need to know, they don't mean the original packet will transmit many times. It just do the fragmentation. So what is the fragmentation? The purpose of the fragmentation is that the packet not over the maximum transmission unit, MTU. So if the packet is too large over the MTU, just like the principle that highways have restrictions on driving speed, there are restrictions on the size of data packets transmitted in the network. So it will do the fragmentation if the packet size is too large. And in here, it is user plane message 1, 2, and 3, and they are composed to the original packet. So how can we know after the fragmentation what is their corresponding section? We can see the section ID in here. When they are in the same section, they will have the same section ID. So in here, they will be divided into 1, 2, 3. And compared to the last figure, just have 3 packets to be transmitted. And my next part is about the express synchronization brain. So in the express, ORAN Fronthaul supports a protocol stack that transmits signals used in PDB or synchronous over Ethernet. And there are 2 types of synchronization. One is for the phase synchronization, and the other is for the frequency synchronization. So for the phase synchronization, it means your phase and your frequency should be always the same at any time. And in frequency synchronization, your frequency should be consistent, but the difference of the degree don't need to be the same. However, in any time, they just need to be, the difference of the degree should be consistent. Like in here, the difference of degree is 180, and here is 180, and here is 180, and here is 180. So how can the ORAN do the synchronization in Fronthaul? They just propose the PTP. So PTP is the protocol to do the synchronization. And what is the benefit of PTP? It has the lower cost and the higher purchase. And there are 4 topologies in Fronthaul interface proposed by ORAN. First, they call LLSC1. It means the ODU act like a master clock and ORU act like a slave clock. So what is master clock? Master clock will send the synchronization information to the slave clock, and slave clock need to synchronize its time based on the master clock. So in C1, they just have 1 DU and 1 RU. The next topology is for the LLSC2. And in here, ODU act like a master clock and ORU act like a slave clock. But in here, they have multiple ODU and ORU. And in LLSC3, it is very similar to LLSC2, except the master clock is located at the Fronthaul network itself. It is not at the ODU. However, there could be some deployment use case that prevent the Fronthaul network from being upgraded and meeting the target performance at the ORU. You can just think that the Fronthaul network don't support PTP or synchronous Ethernet. So to cover this usage case, the other synchronization strategy is they can just connect it to the GNSS. So my next part is about the endpoint. And endpoint will provide a variety of ORU management functions to set parameters on the ORU side. For the endpoint, the ORAN support a protocol stack that transmits signals using netcom over Ethernet, IP, TCP, and SSH. And here are 2 endpoint models. One is for the hierarchical model. In here, ORU is managed entirely by 1 or more ODU using a netcom-based endpoint interface. So DU will do the monitor or control to the ORU. And in this model, it has the advantage of without affecting the currently network system, since ODU support netcom in the endpoint. And the other model is for the hybrid model. First, I will introduce what is MMS. It is the network management system. So for the MMS, it can do the configuration, monitor, update, or check the system have some problem or not. And it can tell the engineer to solve this kind of problem. So For the hybrid architecture, in addition to the ODU, MNS can also connect to the ORU, and MNS is so the advantage of this model is that except the ODU, MNS can also monitor and control other network devices about the uniform maintenance, monitoring, or control. So for the endpoint function, they provide 6 management functions. One is for the startup installation, software management, configuration management, performance management, fault management, and file management. And for the startup installation, you just need to know they just establish the connection between the netcom server and netcom client. It means in here netcom server is for the ORU and netcom client is for the ODU and NMS. And after you do the startup installation, the other management function can be used. So there are 4 steps of the software management. In the first step, the clients will get information on what types of files are currently stored on the ORU. And you will compare with the build name and file name information in the file so that the netcom client can determine whether need to download to the ORU is necessary. After the download, you can do the installation and activation. But you should notice that it don't mean after the installation, you will automatically do the activation. You need to reboot your device and it can do the activation. So for the configuration management, there are 2 parts in the configuration management. One is for the retrieve part. We can use the get config to know the current state of RU. And the other part is for the modify management, modify state. We can use edit config to change the state of the RU. And you may have the question about what state. So there are 5 states of the ORU. In admin state, you can check is there has any resource active. Is there any resource activation is prohibited at the ORU? And in power state, we can change the mode of the ORU. Like if the efficiency of ORU is not very good, we can consider to change it to the sleeping mode. And in upper state, we can reset RU. In available state, we can check if there is the fault as degrade or affect to the RU. And in usage state, we can check is there any carrier is configured to RU now. So the next management is about the performance management. So the purpose of the performance management is to do the collection of measurement result. So it can send a request to say, oh, what kind of performance I want to know. And after he send the request, subscription ORU will periodically notify the performance result to the ODU and NMS. So if ODU and NMS don't want to know the performance result anymore, you can just use the closed session, and then ORU will not send the performance results anymore. So we can know, according to the result, we can know the transmission status, like the power or voltage state. And also we can know the total number of received packet or the number of control packet. Or even I can know the power and the temperature of the hardware. And for the fault management, it can just it will responsible for sending alarm notifications to the DU and the MAS to let they know, oh, I have the problem and please help me to solve it. And in file management, it consists of 3 parts. It is for the upload, download, and the retrieve. So what kind of file we can do the management, or why we need to have the upload and download? I think in here they will have the file like the beamforming configuration or troubleshooting log or trace log, so that we can know the status of the RU. And here's my part.
So let's go. Hello everyone, my name is Nick Huang. I'm going to show you the training course. It's about near real-time RIC. And okay, and this page is the catalog. And in the first, I will introduce the overview and first, I will introduce the overview, and after that, I will discuss the detail, and in the end, I will use traffic steering to be a use case. And the first, what is RIC? The full name of RIC is RAN Intelligent Controller, and it divides into 2 parts: the real-time and near real-time. And the goal of RIC is it based on the information from RAN and use machine learning model or analyze information to configure or control RAN. And you can see the figure below. It shows the co-work relationship between non-real-time and near real-time. At first, non-real-time will get information from RAN, and it will create or choose a training model and input the information into L1 policy and transmit L1 policy to near real-time through the L1 interface. And the near real-time interface, near real-time RIC will follow the policy to adjust RAN parameters. And the next content, we will focus on the near real-time RIC. And then, so where is near real-time RIC? As Jonathan mentioned before, near real-time RIC is between non-real-time RIC and the E2 nodes. And E2 nodes consists of OINOB, OCUCP, OCUUP, and ODU. Okay, after that, so why we need near real-time RIC? Because in the future, there will be more and more RAN and users, and so we need a controller to manage resource and even let network to be more intelligent. So there are 3 top near real. First is the third is resource control. So I'm going to show of near real-time. architecture 那边哦，那还好。
Oh, it's really okay.
Oh, okay. It's okay now?
Yes.
Oh, okay, sorry. We disconnected. So after overview, I'm going to introduce the architecture of near real-time RIC. And the first one is SF. SF is the function in near real-time RIC. According to different application scenario, it will perform the data monitoring and the parameter adjustment of RAM function. And there are two important parts in SF. One is image, and another is descriptor. And the image is a darker concept. So I think Fadeli will introduce it later. And the descriptor contains the configuration data for the SF. Okay, the next part is messaging infrastructure. This part is deal with the messaging interaction in near real-time RIC, and its feature is low latency. So in order to achieve this, there is a mechanism called RMR. The full name of RMR is RIC Message Router, and it's a thin library which allows applications send message to other applications. And RMR provides instruction from the actual message transport system, as well as providing endpoint selection based on the message type. And the next part is conflict mitigation. It's used to resolve the potential overlapping or conflicting requests from multiple SF. And there are many situations, and so we divide into two parts. The first part is direct conflicts. What it mean? When two or more SF request different settings to control target. For example, if me and Jonathan is SF, I ask you to go right, and Jonathan asks you to go left, and this situation will make conflicts. So the conflict mitigation will decide which one is the result. And another part is indirect conflicts. For example, ASF is deal with antenna angle, and the BSF is deal with the measurement deviation. Both of them will affect the size of the boundary, so they maybe will have potential conflicts. Okay. The next part is SF subscription management. This part it will manage the subscription from the SF to the E2 nodes. The basic concept we can check the figure. For example, ASF and BSF they both of them subscribe same E2 node. So in this situation, SF subscription management will merge the identical subscription from different SF into a single subscription to the E2 node. Okay, the next part is management services. Is to achieve the life cycle management of SF and the FCAPS management of non-real-time RIC. What is FCAPS? Is fault, configuration, accounting, performance, security management. And next is security part. Because ORAN accepts anyone can create their own third-party SF. So the security part is prevent the malicious third-party SF from abusing radio network information. And the next part is SDL. The full name of SDL is Shared Data Layer, and it's an API and is used to storing and sharing any data to database. And it will enable the stateless application processes. What is stateless? For example, in the application process, the server won't record the status of the user, and it will reduce the resource consumption. Okay, after the architecture, I'm going to show you the interfaces part. We have 3 interfaces related to new real-time RIC. First is A1, E2, and ORAN. First, A1. A1 is between near real-time RIC and non-real-time RIC. And the main message carried on the A1 interface is policy-based guidance, and it will include machine learning model management. And the second interface is E2 interface. And the E2 interface is between near real-time RIC and E2 nodes. As I mentioned before, E2 nodes, it consists ODU and OCU CP, OCU UP, and OE node B. Okay. In order to realize the near real-time RIC's control of E2 node, E2 node will send some message through E2 interface, such as predefined information or UEID. And if near real-time RIC needs to adjust parameters, it will first suspend the procedure and then issue related policy to E2 node through the E2 interface. Okay. And the next one is OR interface. OR interface is between non-real-time RIC and other components. It's to support non-real-time RIC to achieve FCAPS management, software management, and file management. I won't discuss these too much because it's still defined. It's not very clearly. Okay, in the end, I make a table to show the comparison among the interfaces. We set the center is near real-time RIC, so A1 is related to non-real-time RIC, and E2 is related to E2 nodes, and O1 is related to non-real-time RIC. The basic concept, the basic function of A1 is policy-based guidance, and E2 is support RAM function, and O1 is to support management. Okay. After that, I'm going to show you the components. They they divide the components into two parts. One part is a RIC platform, and another is RIC app. And you can see the block figure. We have already mapped the block figure into the source code file, and in the orange line, the blocks in the orange line, it means the RIC platform, and the blue blocks, it means the RIC apps. And the next content I will introduce, I think is a very important part. The first is the interface termination, and the next is managers. Okay. The first termination I want to introduce is ORAN mediator. ORAN mediator communicates with non-real-time RIC through ORAN interface and explores ORAN related management service from near real-time RIC. And the next is L1 mediator. L1 mediator will deal with the L1 policy process, and to the L1 interface, it will use HTTP, and in the near real-time RIC, it will communicate the payload to the certain SF using the INR messaging. Okay, the third one is E2 termination. E2 termination is the response for routing messages from the SF through the SCTP connection to the E2 node, and it will also use IMR messaging to communicate the payload to the center certain SF. Okay, the managers part. First is E2 manager. E2 manager supports the recall and status for each RAN. There are 5 status. No, it means first, no, it means no RAN in the database. The second one, disconnected, it means connection failed, or E2 termination is died, or the E2 termination is initialized. The third is connected. It means it get a setup request from remote RAN. And shutting down and shutdown, it mean the tail down RAN connection. The next part is routing manager. It is responsible for distributing routing policy among the other platform components and SFs. And the third one is subscription manager. It will manage the subscription and the message routing of the subscribed messages between E2 termination and the SFs. And the fourth one is SF manager. It's used to deploy or undeploy SF, and it will record the SF status and support health check. Okay, we are finished the RIC platform part, and now I'm going to show you the current SF in cherry release. And the next content, I will focus on the traffic steering use case. And in this use case, it will use KPI monitor and QoE prediction and anomaly detection and traffic steering. So what is traffic steering? It is to maximize the QoE improvement of the world's performing priority traffic by intelligently controlling the traffic between multiple cells. Easy to say is handover. And before that, I want to the step by step of the subscription. First of all, if near real time, first of all, E2 node will transmit E2 setup to near real time RIC and let near real time RIC know I'm alive. And if some SF want to describe this E2 node, it will feedback E2 subscription. And if the E2 node accepts that, it will transmit some information, and we call it E2 indication. So this is the co-work relationship with many SFs, and I will introduce it step by step. As I mentioned before, this is the setup. E2 setup part is let the near real time RIC know I'm alive, and the near real time RIC will prepare E2 subscription, and the E2 node will transmit the information. For example, is UEID or some parameters. And the KPI monitor is a SF to get the parameter and put the parameter and the information into the database. And the A1 mediate will get the A1 policy from the real-time RIC and transmit the A1 policy instance through RMR messaging to TSSF. And the TSSF will query the UE signal strength and put the UEID into TSUE list and transmit the TSUE list to QoE prediction driver SF. The function of QoE prediction driver SF is to based on the UEID and use the UEID as a key to query the full data from the database. And then it will give the full data to QoE prediction SF here. And the QPSF will predict and tell TS which UE should be handed over. And the ADSF is to tell TS which UE is an anomaly. And in the end, TSF will decide whether this UE should be handed over or not. Okay, and this is my part. Any questions?
Can you hear my voice?
Yes.
Okay. And you can see my screen now?
I think.
Yes.
Okay. So thank you for your presentation, Nick. And my name is Fadli. And because NIRT RIC use Docker and Kubernetes, we will talk about Docker and Kubernetes. So those two things are correlated, and I will talk about Docker first. So let's say we have a company like this, and usually every time you want to deploy an application to the server, it will go through this process. Development team will try to make the application, and then they will send it to testing department. So there will be two conditions. If it is not working properly, it will go back to the development team. And if it is running properly, it will go to operation team, and they will try to deploy it on the server. Usually, when the development team make an application, it will have a lot of dependencies, framework, and the others. And let's say we give our application to the testing team in a zip file or jar file for Java application. And let's say the testing team installed all of the dependencies already, but actually the version of the dependency doesn't match. So it will make a problem. So instead of giving the application, we can run those applications in a virtual machine, and we can export the image of the operating system, application, and all of the dependencies, and we fix the problem. Now we can ship the entire image of our operating system to the testing team. Now they don't have to worry about the dependencies. But there is another problem. Every time you want to make a new application with different dependencies, we have to export the image, and it will use a lot of resources because every image will have their own resource, and that is why we use Docker. So what is Docker? Docker is an open platform used for developing, shipping, and running applications, and it is called as container manager. Without Docker, we usually deploy our application like this. So every time we want to run the application, we have to install all of the dependency first. But with Docker, we can deploy our application like this. So we will bundle all of the dependencies with our application, and then we can run those bundle, which is called as image. Now, what is the difference between Docker container and virtual machine? If we are using virtual machine, as I said before, we are running an operating system above an operating system. So every time we run the application, they will have their own operating system and with their own resources too. And it is not shared. So this OS here will have their own resource, and it will be slow. Sorry. Okay, sorry. So this OS here have their own resource, and it will be slow. With Docker, we don't have to install different operating system because it will use our currently working operating system here. So every time we run the application, it will use our operating system and with our own resource. Because it will use our currently working operating system where the Docker installed. With this, the application will start with native OS, and the performance will be better because now we can share our resources because we only have one operating system. And what about the security? So those applications still will not disturb the operating system because it is isolated inside the container. And to start, we have to install Docker first for sure. There are some differences if you are installing Docker in Windows, Linux, or Mac OS. In Windows and Mac OS, you can just download the Docker desktop. And for Linux, there are several steps you should follow. And I will not talk about how to install it in this presentation, and you can take a look at more detail at their website. So let's say we have installed Docker already in Linux, and the first thing we should know is container. So every time we run an image, it will turn into container. Let's say we turn the image into container A, B, or C, or all of them, because we can run one image multiple times. And the question is, how do we make a container? So first, before making a container, we can check the install image in our computer using the command here. Docker images, and we can see the result like this. So this is the list of images in my local repository. If we don't have the image that we need, for example, we are trying to run Go language, we can search the image in the repository using Docker Hub from our browser, and then you can use the command on the chosen image, like this one, to pull it. Now we already get the image, and we will create our own image using dummy Go language code. I already created main.go file here, and basically what is this code doing is printing hello world. In this case, I'm making a new folder named as docker-app. So after that, make a new file named as dockerfile, and I'm using this command. This first line here means that we are trying to use Go language version 1.11.4 as our image, and then we will copy main.go from our folder to this directory. And for last line, it means we will open terminal and we will run go run/app/main.go. So next, we will have to build our Docker file, and it will turn into image using this command here. The name of our image will be app-goblang, and the tag or version will be 1.0. And after that, you can see I use dot here. That dot means that I am currently opening my terminal in the same path with the Docker file. To check if our image built already or not, we can use this command here, and we can see that app-golang is added to the local repository already. Now we can start the container using our own image by using this command. This 8080 here means that port 8080 will be exposed to the external connection and will be forwarded to port 8080 inside the container. We created the container already. The only thing we have to do now is to start our container, and to check our container running already or not, we can use this command here, docker container list, and we can see that our image is running. And to access the main.go on the container, we can open our browser and use the port that we already defined. And after that, you can see here that I can see hello world in my browser. It means that it's working. When we are trying to deploy a full application, usually we will not have only one dependencies. To run all of the image and to run the application automatically, we can use Docker Compose. Before we start to use Docker Compose, we have to check our Docker Compose version first by using this to make sure that Docker Compose is installed in our operating system or not. And if you don't have any Docker Compose installed, you can install it using this command here. And now we can create Docker Compose YAML file by creating a new file named as docker-compose YAML. So I make a new folder here named as Docker Compose file. I go into that folder and I make a new file named as this one. And in this case, we will make two services, and we will assign the name as web and database. The image we are using on the first service is Nginx, and on the second service, we are using Redis. Now we have our Docker Compose YAML file, and to check the validity of our Docker Compose YAML file, we can use this command here. And because it has no error, it means that it's valid. Because it is a valid Docker Compose file, now we can run the Docker Compose file by using the command on the first line here. And we can check that our container is running already or not using the second command. To take down all of our running container from Docker Compose, we can use this command. In Docker Compose, we use many parameters, and one of them is setting port. Let's say we want to define the external container port like this. So we will forward port 1990 to port 80. And with the new setting, we can connect to the port with our browser and by running the Docker Compose first. And then you can see here, I'm trying to access port 1990, and Nginx is successfully working. So what if we want to access our custom image using internet? So first, open Docker Hub from our browser, fill the repository name field, and then press create so we can create the repository. And after we create the repository, we can take the image that we want to upload. In this case, we will use app-golang we created before, and you can change this the repository link based on your own link. And I'm using my account, that's why I'm using this link. After tagging the image, we will have to log into Docker first, and then we will push the image to our repository. And now we can check if it is successfully uploaded to the repository or not by checking our account in Docker Hub. And let's say we already made a container. Now we can access the repository everywhere by pulling the image using this command here. So it depends on your repository name and the image name on your repository. And let's say we already made a container and we use MongoDB as the image. We usually use MongoDB to save some data, and if we delete the container, we will lose the data as well. In Docker, we can save the data using storage. There are several storage types, and we will learn about volume. So first, we have to create a new volume by using this command here. Now you can make a new container with MongoDB as the image, and you will use Mongo_data as the volume. And you can start the container and check if it is running by using this command here, docker container list. And if it is running, now you can save your containers data by using the volume that you have created. So actually you can do a lot of things with this volume. You can restore or backup or another else, but I will not talk too deeply about that thing in this presentation. You can take a look at their website. So currently, we already know how to build multiple containers using only one Docker. But let's say, what if we have about 100 containers or 1,000 containers, and then we have to do many things like health check on every container, ensure all of containers are up on every system, or scaling the containers up and down depending on the load. How can we manage that many containers? On this problem, we can use orchestration tools. So orchestration tools is used to manage multiple Docker containers as a single service. And there are two popular orchestration tools that we can use. They are Docker Swarm and Kubernetes. And before we go to Kubernetes, we will talk about monolith versus microservices. So traditionally, our application is a monolith application, and currently it is moving a new trend called as microservices. So monolith application is an application where all of the function is laying on one server only. So it is centralized in one application. But microservices application is the opposite, where we have multiple servers that contain multiple functions, and it will look like this. So what is the big deal? Let's say the load of our server is increasing, and we want to scale up our service. In monolith application, it will be hard to scale it up or down because all of the services are mixed inside one application. In microservices application, it is possible to scale it up manually, but we cannot automatically scale it up or down. Usually, those microservices application deployed inside a container, and automatically scale it up or down, we need automation in deployment, scaling, and management. And Kubernetes is the answer of that problem. Kubernetes is an open source application for deployment, scaling, and management deployment. Simply what we do in Kubernetes is we make a configuration file, usually in YAML format, and then it will send to the Kubernetes master, and it will execute the configuration file and will make some Kubernetes workers. For example, we have two applications, and we want to make 3 nodes of the first application and 2 nodes for the second application, and it will submit it to this Kubernetes master, and it will go to Kubernetes workers. So for the overall architecture of Kubernetes, it will look like this. So this whole architecture called as Kubernetes cluster. So now we will go to Kubernetes master first. Kubernetes master is responsible to manage all of the Kubernetes nodes or workers. This kube API server is an API to interact with Kubernetes cluster. It means all of this architecture. And etcd, it's a database to store Kubernetes cluster data. This kube scheduler here is to assign a specific node to run an application. And kube controller manager here is to control Kubernetes cluster. For example, controlling the node if the node is terminated or stopped. And this cloud controller manager here is the same as kube controller manager, but on the cloud side. Now we will go to Kubernetes workers or nodes. It is responsible to run the application commanded by the Kubernetes master. Simply, it's a slave for this Kubernetes master. This kubelet here, it's used to make sure that our application is running on the node. And kube proxy here, it is as a proxy for our network traffic in the node and can be used as a load balancer too. And container manager, working as a container manager, and one of them is Docker. So first, if you want to run our application, we have to upload the application to Docker image registry in our repository. And after that, we will make a configuration file like this. In this case, we want to run one triangle application and two circle application. And after that, Kubernetes master will run the configuration file, and kubelet here will ask Docker to pull the image that we already uploaded, and it will be run. And before that, what we should do first is to install Kubernetes, of course. And there are many ways to install it, depends on your operating system. So after we already installed our Kubernetes, we will go to Node. So Node is a worker machine in Kubernetes, or before this, people refer Node as minion. First, we will try to take information about our node by using this command here. So we can get our information, get node information about our node, and we can take a detailed look at minikube node by using this command here. And next, we will talk about Kubernetes pod. So pod is the smallest unit that we can deploy in Kubernetes cluster, and pod contains one container. More than one container. Simply, if we run one or more application, it will be deployed as pod. So why we need pod? Pod is an abstraction layer from Kubernetes to make sure that Kubernetes is usable with any kind of container manager. So if Kubernetes smallest unit is container, Kubernetes will only can work with one container manager, let's say Docker. So if we are trying to change our container manager to like Shifter, LXC, or etc., we will not be able to use Kubernetes. That is why we need pod. First, we'll try to take information about our pods using this command. And because I'm not making any pod, so there is no resources found. And we also can try to look in detail about our pod using almost the same command for the node. And because currently I don't have any pods running, it said that pods not found. And now we will try to make a new pod by making a new folder and a YAML file first by using this command here. And I will edit the pod.yaml using Vim. And for this case, we want to make a container with Nginx as image. We write this down on the pod.yaml. Now we can submit our configuration file to Kube API server by using this command. And of course, we can check if it is running or not by using this command here. And you can see that our pod is running. To look a little bit more detail on all of our pods, we can use this command here. We only add -o white, and we can see at the IP node, nominated node, and readiness gates. And to make sure our pod is accessible or not, we can use port forwarding using this command here. And I'm trying to access this port. And because I can see the welcome page here, it means that it's working. So we will go to the next one and we will talk about Kubernetes label. So label is used to make some additional informations, and we can put the label in replication controller, replica set, service, and etc. To make organizing our pods easier, we can use this label. First, we can open the pod.yaml we made before using this command here. I'm using vim. And now we will make some labels to our pod by inserting this string in metadata part. So I'm inserting about 3 labels here with their value. And we can create the pod by using this. And to check the difference with the previous one, we can use this command here. So we have to add this show labels. So now we have 2 different pods running. This one without labels and this one with labels. And to add label, when the pod is already running, we can use this one. And to change label value, when the pod is already running, we can use this one. So this label is useful when we have a lot of pods running in our PC. Let's say we want to check pods from R&D teams, and we can use this command. We cannot find any pods related to R&D team because we don't have any pod where team equal to R&D. Now we will check every pod belongs to finance team by using this command here. There are actually a lot of query combination we could use in this case. When there are so many resources in Kubernetes, there is a high possibility that we will use a same pod name. For example, we are working in a multi-tenant environment and we want to deploy a pod named Nginx to more than one team. In that case, we can use namespace to make it possible to use a same pod name for different teams. And to check currently available namespace, we can use this command. And this is the list of the namespaces. If we are not assigning any namespace to a specific pod, it will assign to default. And we can check it by looking at the detailed information of one pod by using this command here. And you can see at the namespace here, the value equals to default because we don't specify the namespace when we create this pod. And to take a look what is inside default namespace, we can use this command. It is the same as kubectl get pods because defaultly our pods will use default as their namespace. To take a look what is inside kube system namespace, we can use this one. And now we will try to make a new namespace by making a configuration file named as finance.yaml. We make a file and we will edit it using vim. And to make a new namespace, we should put this in the configuration file. It means that we are making a namespace and we will assign finance as the name of our namespace. And now we can run the configuration file by using this command. And if we are creating a pod using this command, we have an error because we are making a new pod with the same name with the same namespace. But if we create pod.yaml with different namespace, it will work. We can assign namespace to a specific pod by using this command here. You just write namespace and the name of your namespace. To delete namespace, we can use this command, but be careful because all of the pods linked to the namespace will be erased too. The last thing that I want to talk is to delete pod with query. If we are only deleting one pod, it will be easy. But what if there are many pods? We can use query that we learned already at Kubernetes label to act as a selector. And to delete one pod, we can simply use this command. And let's say that product team is not using Kubernetes anymore. We can easily delete every pod related to product team by using this command. So simply we are using query here. Or maybe we want to delete all of the pods using default as namespace. We can use this one. And if you want to learn more about Kubernetes or Docker, you can check at my notes. Here, you can just click at the link on the presentation slides. And I have attached the link here, so you can access it. So thank you for your attention, and we hope it will be useful for you guys. Good afternoon.
Okay, does anyone have any questions for today's training course? You can type in mode or just say it. No one. Oh. Fronthaul interface. Okay, Suha.
Nadif.
Oh, nothing. Oh, Docker. So,
Fadli.
Sorry, there are some question on the chat box, so please check it and answer the question.
hello, Fadli. Can you answer the NUM's questions?
Oh, okay. Wait. Culture. Okay.
We also have another question from Suhua, to Suhua from Wito.
What is
Maybe
some
for
number
Nadif.
and how did the Oh, so I'll answer the question from Huainam. So could you let me know what is Docker images? So Docker image is a read-only template that contains a set of instructions for creating a container. So if you have an image and you run it, it will turn into container. And image, actually, there are a lot of image we can make. Let me show it. Wait. You can see my screen?
Yes.
Oh, okay. So, for example, we are trying to build a website and we want to use MongoDB as one of our website dependencies. We can just search at the image here. Let's say we want to use Mongo. And then we can use this command here. We pull the Mongo image and then we can run it on the Docker and you can link your website to this Docker. So basically, image is like your dependencies. Is it clear? Is it okay? Okay. And what is the maximum number of container? Actually, this one is it's based on your hardware. The number of containers. About this question, maximum numbers of containers, it depends on your hardware. And how the Docker can manage their nodes. So in Docker, in native Docker, actually, we don't have nodes. Nodes is a term used for Kubernetes. So Docker only use container, image and container, and they manage their container, not their nodes. So this nodes term is used for Kubernetes only. Yeah. It is clear? Okay. Is there any question? You can just ask. Oh, sorry. Possible to specify a local IMS.
Is Suhua there?
Oh, okay. Rodriguez will ask, is it possible to specify a local image in Kubernetes pod, or will I need to upload it? So actually, from what I learned, we have to upload the image first to the Docker Hub or the cloud, because it will have, there's the flow. They have to check to the image repository first. Like, so for the workflow, you have to upload it to the image registry first, and this image registry is an online repository. So you have to upload it first to this registry. Is it clear, Rodriguez? Okay, you're welcome.
Maybe I also want to answer a question from Professor Ruki, Mr. Ruki. So actually, some of the part of the ORAN, for example, the RIC codes or RIC image, we can pull it from Docker image. So like we can, they use some methods which we call as Helm. So we can get the image from server. But for the ODU, they have Docker image, but we haven't tested yet.
Oh, thank you, Jonathan, for answering that question. I didn't saw that one.
Oh,
So how do you understand it? Do you understand the answer?
So any other question? If you don't have question, I think we can close the meeting today. So if you still have question, you can just draw us an email or write some your comment on the page we share you for the training course. We will try to answer it later. So thank you. Thanks for our speaker today, and thank all of you for your participation. So looking forward to see you soon. We hope we can have other training course quickly. Thank you.